Okay, so, oh man, no connection. Um, However, we should probably first, we should probably first finish the last two projects which we were discussing last time. So it was it was here, right? So I put the list of potential. Oh, man, still sharing this. Just a sec. So I put the list of potential projects here on the class webpage, so you can click and go ahead and revisit what we were talking about last time. But the point is that I wanted to just quickly discuss the last two in case someone wants to do them, and then we'll move into security. So these two are, I mean, equally exciting. So the fact that I'm discussing them today shouldn't diminish their kind of elegance in a way. So this first one on performance analysis of cherry morality. So did anyone, maybe besides Jerry, ever looked into cherry morale or in general cherry architecture? Jerry, okay, so you know. Cherry, do you think you can, I mean, first of all, I will give lecture on cherry a little bit later, but at a high level, the idea is that in this architecture, every pointer, instead of simply containing like an address of the whatever object on a heap, right? It also contains the bounds. Meaning that if you try it, like, and the pointer is like, if this is 64 bits, the whole pointer is 128 bits, right? All the register set, everything is extended with those additional fields which allow you to reason about the bounds, right? And so if you try to use this pointer and suddenly you're doing an offset operation from this pointer beyond the range of this object, you can simply get an exception on this architecture. In the end, what it allows you to do, like imagine you have a system which owns the heap, right? So like if this is the entire heap of the system, let's say of a process, for example, your goal is, for example, to isolate a library. Let's, for example, say that you running some untrusted code, something like old implementation of some kind of a JPEG reader or something like that. Normally, and we're going to talk about it today, it's easy to confuse this library, which is in security terms, find an exploit, to, for example, find an error in the program in such a manner that this pointer, which JPEG uses, points to some sensitive object on your own key, kind of like a security key, for example, right? But Cherry Marella allows you to specifically say that, by the way, this library JPEG can only own objects, for example, in this region of the heap. In fact, every object which it can own is explicitly pointed by a capability, right? So you cannot confuse the pointer into pointing into some region of memory which wasn't originally granted to this to the domain of this JPEG code, right? And so the question, however, is how much overhead it introduces, right? So in this project, Morella actually has it has various ways of introducing isolation. And we're going to talk about it maybe like within a couple of weeks, which will be too late for you if you take this project. The question is like, For example, in the function calls, which are strictly controlled by capabilities as well, meaning that you cannot just like randomly jump to use a jump instruction to transfer control flow to a random place in memory. You really need a capability or this memory pointer with proper bounds to start executing a function. In this project, it asks the question, how much overhead that really introduces. And we have a physical cherry machine in the lab. So in this project, essentially, what you're going to do is you try to, first of all, understand what cherry is doing, how it can introduce isolation, and also like measure those overheads. And the reason why is it an appealing project? This project is interesting because, for example, variety of institutions, and specifically this the first cherry prototype, which is Morello, is implemented by ARM. So there is a chance that cherry will show up in mainstream CPUs. So this Morello board is a real silicon prototype. So it's not maybe as well optimized as your commodity CPU in terms of like, pipeline and everything, but it's reasonably fast. And British government is aggressively pushing cherry as a security mechanism in our system, and why it will probably become clear in the next couple of lectures, but still it's kind of fun to know the internals of this architecture. So this might become the de facto or a popular mechanism, especially if ARM fully embraces it, right? Okay, so any question about this? And I understand that it's probably not very clear what I mean with all these capabilities and stuff, but we will talk a little bit more about what it means to exploit something today, and so it will become more clear. And if since I brought up cherry, every time I can talk about a specific exploit, I can actually say, what do you think will cherry stop it from? Right? So that's project about cherry. And finally, my final idea, which is also kind of interesting, and again, remember the first part of this project set was more about performance, like kind of scalable buffer cache, something. But the second part is more about security. I mean, literally in systems, you often get paid to improve performance or improve security. It used to be that you also you were working on improving reliability, but roughly speaking, those are the three, right? Okay, and security and reliability kind of can overlap some, not fully. Okay, today we're going to talk about kernel exploits. And essentially, when an attacker finds a way to exploit the running kernel of a Linux machine, this exploit is assigned something what is called CVE. What it stands for? Common Vulnerability E. What is E for? So CVE is like every time you really say, okay, I found a bug in. Did you look it up? Common vulnerability and what? And exposures. Okay, CVE. So it gets assigned a number. And so it's kind of like an official designation that this is a specific bug in your kernel code. And again, in 5 minutes, I will go back to those bugs. It will become clear. It leads to an exploit. Okay, nice. Again, later today, in just a second, I will tell you that Linux roughly has between like 200 to 600 exploits every year. Some of those exploits, and it's always debatable because it's very hard to analyze carefully the impact of an exploit. Why is that? Because a very careful and skillful attacker can use seemingly benign errors in the kernel to gain full control over the machine, right? Again, we'll talk a little bit about it today and in the next couple of weeks. Okay, cool. So we have, roughly speaking, let's say maybe this year is an outlier. Last year, I think it was around 200 vulnerabilities in the Linux kernel. This year, it's 600, a lot because a lot of security teams are working on it. However, the question is, I kind of claim that it's only a tip of an iceberg. And in reality, almost every bug fix in the Linux kernel is an exploit. It just never gets assigned a CVE. Like literally, you find a bug in your code, I kind of claim that you can exploit it. Maybe the attack will not be like, will not lead you to a full control over the machine. Maybe it's just a denial of service. Maybe you just trigger a crash and the machine has to reboot, right? For example, it's still an attack. Imagine you're like attacking, I mean, I don't know, web servers on Amazon, or they're like, just because you're sending some maliciously crafted packets, right? Machines just start rebooting, right? So it's an attack. So this project asks a question is, what fraction of Linux bug fixes really gets assigned a vulnerability? And the expectation is that it's a tiny fraction. And really, I mean, I don't really know how to answer this question trivially. Like, you can just start looking through commit messages and see what people are patching in their code. Like, you take a device driver, Linux kernel, let's say, I don't know, like NVMe driver, we talked a lot about it. Look through the commit messages history and see, okay, they patched something. It looks like they patched a pointer or like a bounce chat, right? And well, you say, well, but it never get assigned a CVE, right? But it's really a CVE. And then a more interesting approach to do it is to come up with some kind of a static analysis, essentially automated system, which first parses the logs, but also like compares the diffs and makes a conclusion that specific change is likely an exploit. So that's also interesting. So because then we can say, look, in reality, there is a way higher number of those exploits in any system, probably not just Linux, but everywhere. But again, it's a research question, so I don't really know. What I've heard recently is that it used to be that Linux developers, when they assign a CVE, there is also a severity score. Like it goes from like nearly benign to something like full control over the machine, right? And people are always debating like what score to assign. And like recently, I think they made a decision to assign each vulnerability a highest score because they don't have the resources to understand whether something can get exploited or not. And it's like it's really like it's an art. So like some of those sophisticated exploits, they stitch multiple attacks together or multiple flaws in the code together. Like famous competitions like Pound to Own sometimes have like 14 steps to escape the Google Chrome browser, but they are like extremely elegant in how they are implemented, right? So in theory, a lot of those bug fixes can be, or vulnerabilities can be exploited to gain the full control over the machine. Okay, so this is my list of projects. As I said last time, take a look. So, and I will assign, let's say, a homework assignment, but really somewhere by early next week, you should at least commit to one, right? Feel free to form groups. And again, like, don't get scared. So they're hard. I kind of agree. Those are research challenges. And that's kind of the goal, to expose you to those research challenges. But even if you have like make a couple of first steps towards solving one of those, I think it will teach you a fair amount of things. So that's the deal. Okay, cool. My second thing today, I wanted to remember my next homework assignment, which I'm gonna assign, is to essentially paravirtualize x86. So let's play this game. Let's discuss it in class. So I don't know, like if you have a laptop, probably open it up. So let's discuss in class, what does it mean to paravirtualize x86? So at a high level, we want to be able to run, like come up with some kind of command inside x86 or a system call, if you like, which allows you to start another copy of x86 as a virtual machine. When I say as a virtual machine, we can do different tricks. We can say, look, we can either use, we can technically speaking write an interpreter, or we can write a JIT compiler, or we can use VPX, like hardware supported virtualization, right? All of those choices are kind of the same. But just to make sure that we understand the most of it, let's do it Zen style, meaning that I want to come up with a way to run x86 kernel as one or a collection of processes, essentially Like if you have an x86 kernel, this one, I want to run another x86 kernel, modify it to make sure that it runs as a process. Let's say Q1. And maybe if this one starts another process internally, we can talk about how to do it, but maybe for the sake of it today, just to make sure that it's doable, we can maybe run it as yet another process in the original version of the system. If we do it, okay, what do you think needs to be done? How can we approach this? That's kind of the reason we spend time on it, because we spend a fair amount of time doing virtualization, right? So we went through all these possible solutions. It's nice to do something, like kind of make sure that we understand how it can work in practice. What needs to be done to this x86 virtual x86, we can call it x86 PV kernel? What are the changes? And what is the general architecture? How can we run it? What's PV? Stands for para virtualization. The para because it's not full virtualization. It's kind of like only partial. Like meaning that the kernel is aware of the fact that it's not running on real hardware. It runs on another x86 kernel. So for example, we can introduce a new system call, which will do something like change or switch CR3, for example. So let's start. So what are your ideas? What do we need to do? Well, okay, good luck. Port QEMU to x86. But again, it's like, I mean, I have an anecdote, which is usually like, I should probably refrain from anecdotes, it's personal stories. So anyway, so my kids are alpine racers. I mean, good skiers, let's put it this way. And I occasionally participate in those ski tuning practices. That's essentially the coach invites the parents to teach them how to tune skis, because we have to tune a lot, sharpen them to make sure that they can, I mean, they ski on ice, literally. There's competition hills there, like they spray them with water. And so I go there, learn how to tune skis, I'm reasonable at this point. And at some point when I asked them, okay, there's this funky machines, you buy kind of an electric thing, which you run it along the ski, and it supposedly like tunes it automatically, like kind of magical. So that's the QEMU example. And I asked the coach, okay, can I buy one of those and be happy with it? And they say, well, yes, you can. It will tune, but it will only do one job. And unless you understand what you're doing, because you will never learn, because you just will be always, you only know the effect, you run the machine, the ski is sharp in one specific way. And so QEMU is this kind of tool. If you simply run QEMU, you're not going to learn much. If you say, look, I want to do a deep dive and understand what QEMU does inside, and I can build the QEMU, specifically a minimal QEMU version for this specific task, that's okay. You can, I don't mind it. But the reason I chose para virtualization and for this assignment is to make it, it's kind of easier to get the transparency, because with QEMU, you will achieve the same result. So kind of like when you tune a ski, you go with like with a file and with a stone, and then you like judge what kind of terrain you're going to be skiing on. And the funny part is that if the ski has like kind of this rectangular shape, unavoidably when you tune it, like when you sharpen a knife, there will be overhang here, and you have to decide what to do with it. Like if it's too big, it can break, and then you like end up with a dull ski. So same with QEMU. So just let's be more careful. Let's just build the minimal set of things which we need and nothing else. And if you want to build QEMU, we can, but then it's a different story. Let's do para virtualization today. Well, my suggestion is to open the QEMU source code, right? Not QEMU, the x86 source code, right? Why not? Because let's say we go to something like this, and we say, let me make it slightly larger just for you to see. No, probably something like entry.s is an entry point of the kernel, right? Do we remember what is this business? So this is literally where x86 starts executing in this line 45. I mean, we can go about it differently, right? About this task. I can go backwards because I kind of know high level what is it I wanna build here. Or if you don't know what to build, you can go low level and just like literally think about what is it you need to do with every line, right? So, okay, cool. So here it says, okay, we need a 4 MB pages, right? Then we say we're gonna use this page table directory, entry page table directory, which comes as part of the kernel. We will load it into the CR3 register. We will, Then you will turn on paging by setting this flag in CR0. We'll set up the stack, right? By, again, just assigning a value to the ESP. And then we'll jump to main, right? And that's after the fact that the kernel is actually loaded in this memory. I just skipped it for simplicity right now. We might revisit it. So imagine we already loaded, like we used like exact system call in x86, which loaded the image of the kernel in the memory of this new process, which is running inside x86. What is it we do with CR3 and other things? What is the suggestion? What was Xen doing? Do you remember? Set up a shadow page table. So how do we do it? Just be a little louder. Oh. Otherwise, okay. So cool. Then we say that this paravirtualization interface will include an array which will keep information about every physical page, or we'll call it machine frame number, which corresponds to a specific index for the physical frame number of this x86 kernel, right? So, okay, what we're gonna do with this array? We can think about it. So we say, look, this line loads the CR3, right? Okay, so we say, look, we will add a system call to x86, something like set CR3, right? What will be the argument of this system call? Our intent is to say, okay, cool, please like use a page table controlled by us, right? So what should be an argument here? Yeah, I agree with you. Good job. So you say a page table will be a physical frame number, which is actually points to an entry in this array, right? And okay, because we're saying, look, please use this TR3, right? Agree with this. So this page number, our intent is obviously to make sure that this page number contains the page table, right? In this example, it's an entry page here, right? It's just one page because we said, okay, by the way, we're going to be running on 4 megabyte pages, right? So it's a slightly simpler page table, right? Agree? That's okay. So the question is like, what will be the entries in this page table? How do we want to organize the address space? Do you understand what I'm trying to ask? So if this is your address space, starting from 0 to 2 gigabytes, those are the user addresses. And addresses above are used by the real x86 kernel. It probably makes sense for us to put our power virtualized kernel in those addresses. Because then we can use like the first gigabyte of this address space for user addresses, for user processes. It's okay to change. You can say, look, we can later like remove this limitation. But if you want to run like a PV version of a kernel, it can sit in like above the first gigabyte, just for the sake of exercise, right? So for example, this entry point of this compiled kernel, if typically it's like, remember, it's typically somewhere over here, which is 2 gigabytes plus 1 megabyte, we will set it to like exactly 1 gigabyte in our power virtualized scenario, right? You agree? However, there is another problem here. If we just blindly do this game with entry page directory, it's probably possible, but maybe we don't even need it because we're already running on some page table when this process is created, right? So why don't we assume that when the process is created, it already has a page table and it's like a regular 4 kilobyte pages. It sits in CR3 register used by x86. Obviously, this memory, which is like all of this memory, is mapped as with the user bit set in a page table, right? And so we say, look, we said that since we're how do we want to do it? We, for example, say that this page table maps, imagine we give this kernel, let's say 128 megabytes of physical memory, right? Which means that those pages are already allocated when we started the process, right? And the question is, no, we can do different choices here. So let's assume the kernel. The question is like, how do we want to construct this address space? There are multiple ways. So I was rooting for this one, but that's maybe that actually kind of like complicates the deal because, although maybe not, you can already imagine that the page table on which you start already maps the 128 megabytes into your address space, which means that like you already have a page table. It already maps something from the first gigabyte to first gigabyte plus 128. And you can probably even completely skip this code altogether because it's just part of the booting process, right? And then we can move on to what will happen later in the kernel. So just imagine that your address space, let me make a drawing of it. If this is the user address space at this point, we can say that at the first gigabyte, 128 megabytes of memory are already mapped by this array. And to be more specific, this array has to be way larger, right? So it's like it covers like this is below the 120 below 1 gigabyte, and this is 1 gigabyte plus 128 megabyte. Although these entries may be potentially empty, right? For now, for example. Although, yeah, that's just fine because you say that your boot code, for example, just completely does this mapping. So already, like, hold on, your array is actually the total array is 128. They're just mapped with a 1 gigabyte shift, 1-to-1, for example, by this page table. Does this sound like a good idea? Then when you like essentially this page table on which you're running says your kernel, your entry point is right here, somewhere the first gigabyte, and like essentially you say this is my virtual memory for the kernel. This is how I start. That's totally fine with x86, although some changes are needed to implement this gap but that's fine in a virtualized process, right? Does this make sense? So for example, we don't know where this page is pointing, like what physical number is here. So those are like all over the machine memory, right? So it doesn't matter where these are. We just know that when we start on a page table, when we start with an entry point, the only region which is mapped is from 1 gigabyte to 1 gigabyte plus 128 megabytes. Make sense? So which means that you can compile the kernel and you start executing and you do like essentially none of it matters. So this code goes away completely, but you simply say, look, I will set a stack, and that's fine, you can do it. And you essentially at this point jump to main. Right? And you start executing essentially your boot code is very, very tiny. You from entry, you just jumping immediately to main. And you start running in main. Does it make sense? Agree on our, like what's important here is to converge to some kind of virtual memory organization. And I say, look, we're not going to worry about this set CR3 right now. Imagine we are running on some kind of a page table which is created by us, and we just know that it's there. And it will be our boot time page table. Good. Although we can always like rearrange the page table and remap something, but for now we just say, look, it's all mapped. That's essentially what we did. We achieved this, the mapping which x86 always wants to achieve. So it's remember, it tries to remap all available physical memory starting from the second gigabyte to the fifth stop. And in our case, this fifth stop is 128 fifth stop. And it's already mapped by the syscall, which like essentially we have to introduce a new syscall, which says instead of like doing exact, it will do exact into PVM, our virtualized VM, and exact into PVM construct this page table and address space which we want for the sake of it, right? Does it make sense? Okay, cool.
What's P2?
P2, no, nothing. Like that was a discussion about potential, like how we run processes and whether we virtualize through QEMU or we virtualize by like introducing virtual extensions to x86 kernel. So I'm changing like slightly the kernel, but not much. Essentially, I just say, okay, I don't care about this code. My kernel is compiled to run at 1 gigabyte. So this entry point is 1 gigabyte. It's virtual addresses. We assume that, like, remember that the boot, before we ever get to this code, our boot manager switches into, actually, no, we switch into paging only here. So like we were running the segmentation on, and like essentially we say, but we're gonna imagine we're already like running this paging on, and there is a page table which sits which is created by the system call, which we add to x86, right? Let's quickly get into main. What's next? My goal for you, I mean, I provide you an outline. I want this to be written as an answer to an assignment with some level of details about what the system calls are doing. And like the reason I discussed that's one possible virtual memory organization. We might want to revisit it, but let's keep going with this design. What do we need to do here in main? Anyone remember 626 good enough?
Well, because that PVM is when should we call this? We should not call this now, right?
We should not call what?
PVM because that PVM.
Exit PVM is called by, let's assume from shell. It's a new system call which you add to x86. You say it's a new system call which allows you to create a special kind of a process. It's not a regular process like another like utility like cat, for example.
So we use this to load or prepare this virtual memory, right?
Correct.
Instead of static.
Right, correct. Although we can come back to it in a second and decide what is that we want. Maybe we will change slightly, but that's one possible organization of how we want to do it. What do you think the next steps? At this point, my suggestion is to skip the middle and think towards the end. In the end, our goal is to enter this function and forget about booting multiple CPUs, multiple processors. Our goal is to create a first user process, and then at some point switch into the first user process. Right? Question is how? The question is, how do we want to run user processes? Our goal is to make sure that user processes are somehow isolated and cannot override the kernel by a straight memory write, right? So what are our options? Say again, Jared, you protect the kernel memory. Do you remember how Xen does it? I mentioned it. So really, you need some kind of a protection within the process. So how can we do it?
Use implement segmentation. Post and then like basically the kernel memory in the guess will be like in like a higher rate. And you just like switch those out.
I think you have a good gist. So, and if you think about it, you will figure it out. Let me help for a second. There are multiple ways. There are essentially two ways to do it. And we can choose the way which we like. I just, again, wanted to go step by step to make sure that we understand that there are multiple goals about it. So one goal is to place this user process inside the memory of another process. Like literally, just it's physically will be a different page table. But so essentially it will be sitting here, starting from address 0, going to address, let's say we said 1 gigabyte, right? Agree? we'll be using a different page table. We will be able to control the page table from the VM process because it's a special VM process. We say it's a VM kernel, let's say. And this process is, let's say, VM user. And so, for example, when this kernel wants to create a page in this process mapped at address 0, it will use an explicit system call to say, wow, please use one of my pages, which I have here. I know that it's mapped. I know that my kernel, which I've loaded and booted, added those pages, which correspond to those ones, to my memory allocator. So use one of those pages, that's say machine frame number 8, and map it into address 0 of this page table. Agree with this? This page is still mapped here, right, in my virtual address space. So when you say I want to write code into this page, since it's still mapped, it's not mapped by both page tables, this orange one and the yellow one. It's just the yellow maps it at address 0, and the orange one maps it at address, I don't know, somewhere above the 1 GB plus 128 megabytes. So in the range between 1 GB to 1 GB plus 128, right? Agree? So you can map CPI something into this page, and the data will show up here, and then you can set, for example, registers and everything, and start and say switch to that process, and that process will be running, right? And it cannot access anything because the only pages, which is like at this specific example, it maps just a single page, right? Agree? Like, is this trick clear? So we're saying that we're gonna be using 2 different page tables, one for the kernel and one for the user, right? Why is this? It's a little easier, although your trick with segments, where you say, look, if alternatively you can say this runs in ring 1, this runs in ring 0, and this yellow code, if we place it in the same address space, runs in ring 3. Then we configure the segment of segment of ring 3 doesn't matter, it can span the entire address space. The pages of this one is mapped with user accessible bit. User bit is set to 1. And the pages of obviously ring 1 is just ignores this bit, so it just accesses everything, but its segment runs from 0 to 1 GB, I apologize, 1 GB plus 128 megabytes, which means that the kernel itself can access anything from 0 to the upper limit, which is 1 GB plus 128, but cannot access the real kernel, which sits in ring 0, which starts at 2nd gigabyte. So those tricks are equivalent. So do you understand that you can go either way? Which one do you want? It doesn't matter.
So result ring 0.
You mean you can map the real host kernel?
No, so for the guest, we just run one process, both user. Kernel.
Meaning like temporarily essentially delete those entries which map the kernel, right?
Yeah, or just
Yeah, so kind of set them to inaccessible. That's also a trick. I agree. That's probably doable. So essentially you temporarily, when you kind of like, when you do a system call and exit from the guest kernel into guest user, you essentially say, wow, before doing that, you go into the main kernel, erase this entry or temporarily make it inaccessible to make sure that the whole address space, which is starting from 1 gigabyte to 1 gigabyte plus 128 disappears from the page table. That's a trick, doable. I don't mind it. That's a valid trick as well. In practice, I think the fastest trick is a trick with segments. The second fastest trick will be a trick with running two different page tables. And the reason for that is, remember, I mentioned once that modern CPUs implement tagged TLBs, meaning that you don't have to flush the page table. And then when you're doing this trick, if you're removing the entry from the page table, you have to flush the TLB, which will affect you. But probably if it's your last resort and nothing else works, or for whatever other reason you choose to do it, that's doable. It's just probably the performance argument. So this trick with rings is especially fast, and this is why Xan was promoting it. It's a little bit like, it's more involved. It's exceptionally fast because you can even do the syscalls between rings 3 right into ring 1 without even exiting into the host kernel, which is additional kind of benefit. It's like almost like as fast as in real hardware. Whereas when you switch between the two page tables, your syscall is really like going into the host kernel page table switch, which is on tactile be still like, roughly speaking, it's 400 cycles to do this one-way invocation of a syscall. Versus here, it could be like in the orders of, yeah, it depends on which mechanism you're using. So probably roughly the same, actually. Did you guys still follow? So let's, again, the segmentation in your homework, you're free to choose whatever, even your trade, Jerry. I'm happy with it. Just as long as you understand it. I'm glad that you're suggesting like a completely different trick. But let's go for the sake of it with two different page tables. It's just a little easier to explain for the sake of example, like this today in class. I will ask you a question. Do you understand the trick with these two page tables, right? Or any questions about it?
If another process comes, it will be
Third page table. But that's okay, right? So like it's not like there is an overhead associated with it, but not huge because every process will have its own page table anyway, even in the original x86, right? So you just added one extra page table on which the kernel is booted, and on which it's like it's this kind of, I forgot, I don't really remember on which page table x86 is running when there are no other processes. Imagine everything just exited, the page table. All the process page tables are deallocated. We can kind of revisit it in a second, right? But you're right. The reason I started, okay, remember I said we're gonna go a little backwards because we said, okay, this is our setup. This is how we want to run a process. So the process will run as a separate process on the host system. By the way, the reason I'm also explaining it, I forgot to say, is that this organization, in fact, yeah, this organization is used by something what is called user mode Linux. We probably heard of it. You can run Linux on top of Linux, and this is exactly the trick. So, I mean, I say exactly, but close enough. So essentially, there is a mechanism which allows you to kind of like route the syscalls between these processes which implement the process of the like this virtualization solution exists for real in the wild. I think it's called user mode Linux, and the second is UML. Again, there are literally two projects. One is called UML, stands for user mode Linux, and another one is Linux, which stands for something like user mode Linux. And they slightly differently, like one of them might sacrifice the fact that there is isolation between the user and the kernel in this scenario. Just there will be no isolation. They will be just running on a single page table. It's still good because if you like run some scenario in which you run one application which you trust or not trust, but like that's your unit of isolation. So it's kind of like a library operating system. We'll come back to it in a second, like in the next couple of weeks. So you'll see why it's useful. But okay, we want to like full virtualization with respect to isolating processes. So we said, okay, we're going to run each time you want to run a new process, you will have to kind of create a new page table, and this paravirtual kernel essentially knows about it. So it says, we'll add a specific new system call. So somewhere, like for example, when you create inside this user init, let me see, this doesn't want to grab. I just wanted to go quickly up. Wanted to go to this function user init. So somewhere when you create a new process, normally what you do in x86, you use this function init UVM, which initializes user virtual memory, and you say, look, instead of doing this, what I will do instead, or not instead, but you change this function. So this one just says, okay, that will be my page table directory, right? So you say, look, where does it get the page table from? So it has to allocate it. So to see it. Each process has a pointer to a page table. So you essentially say inside this, what do I do? Maybe. So you already like running with this with the page table. I'm a little bit confused on what is this mem? Why are they allocating mem here? Okay, it's just to map the init code. But the point is that every time you will be creating a new process, you will kind of, instead of just simply, if you have something like in x86, you have something like proc, which you have array of processes, right? This is a process data structure. The process data structure, this proc, will have a pointer to the page table, so to the root of the page table. So instead of simply allocating this page from the memory allocator, you will need a new system call. And the system call probably should be something like, take one of my pages, because, and say this is a machine page number 77, and register it with my virtual machine as the root of a page table. Because this thing says, okay, look, I remember later on, in fact, maybe you don't even have to register, because the question is like, why do I think I want to register with the host kernel instead of like every time I want to switch between process, I can say like I can introduce some syscall kind of like switch CR3, like essentially, and this will, like as you mentioned, or you maybe you set a machine frame number, and this will be a new page table for this yellow process here. So what's wrong with this approach? Just blindly every time I'm switching between process, providing a page, which is the root of the page table, and supposedly it will lead correctly to all the leaves, right? Everything right like that. So why do I want to register a page table with the host kernel? Well, if I blindly ask the host kernel to switch to this new page table, the host kernel has to validate that the page table is constructed correctly. That it, for example, doesn't try to map the host kernel's memory as accessible to the user, right? So one way to do it is on every switch, do this verification. So kind of like walk this page table, which the guest suggests to use, and say, look, like do verification, but it's expensive because you have to scan all the entries and check that they are well formed, right? That's expensive. An alternate way is to somehow say, look, use one of my pages as a page table, and then maybe at this point, the host like makes it as read-only for you, making sure that, okay, you cannot modify it explicitly. You just said, okay, I provided the memory where I will be keeping a page table. Originally, it's empty, so verification is trivial. You just set it to 0. And in order to essentially to change this page table, you will have a system call which explicitly maybe either like maps a leaf, and that at this point you're gonna make a leaf as read-only, or maybe it explicitly even maps a virtual address. And then the question is like how the host resolves if you need to allocate additional pages in a page table. Maybe, you know, like it can either drop them from here, but that's a little weird because the guest will not know which page to give. So most likely you will want to come up with some architecture where you say, every time I want to add a leaf, I will explicitly add a leaf, like saying that if this one was my page table directory, I want to say your system call, which the host kernel exports to the virtualized kernel, is to essentially kind of like write page table directory PTD entry. And you say, look, I'm writing entry, let's say 11, with the machine frame number, let's say 15, adding a new leaf to the page table. And at this point, the host says, okay, look, I will mark this one as read-only as well to make sure that you cannot directly manipulate the entries. And the only way for you to do this is to like go into this leaf. And if suddenly you're trying to like, for example, you can say something like, right, the question is like, what's the system call which updates this entry in the second level of a page table? So how do you want it to look? So the first level of a page table is easy. You say write page table directory entry. How do you write this entry? What's the syntax of this system call? So here I said, okay, just write page directory entry. By the way, you might want to even say that entry, since you will have multiple page tables, you will probably need something like identifier of this page table itself. So remember that this is the root of the page table for the yellow process, but maybe we'll have a green process which will have a different root. Maybe this one is like entry number, machine frame number, let's say 7. So you will take 7 for this for a specific page table, and then you will say, I want to write entry number 11, and what I want to write here is like value 17, right? So it's like this stands for the page table, like stands for the root, this stands for the entry, and this stands for the actual content or the leaf. But what if you want to write this entry? Like kind of you have to ask the host to traverse the page table to reach the specific number. So instead of like providing entry 11 in this new system call, which you say write page, not page table directory entry, but page table entry. And you say page table root is the same, stays 7, right? But now what is this argument to reach this entry? How will you encode it? It's relatively easy, guys. Remember that the page table, how is the CPU encodes those entries? So 11 stands here, sits in the top bits of an address, 7, like, and if you want to write, since you wrote here, whatever this entry will be encoded by this number, for example, and the host can traverse the page table, say, okay, wow, this entry number 17, are we like, what is it pointing to? Like, first of all, if this entry is not allocated, that's an exception, and it will probably terminate the VM. But if this entry exists, then you can write something here, and this, like, essentially address, you just make sure that the page belongs to this VM, right? No, essentially, okay, at a high level, you don't have to follow my specific interface. What you need to figure out is an interface for how to modify entries of the page tables, right? It can be anything. So you can, like you say, well, probably this is, I don't see an alternative, but that's essentially what's going on here.
When should we need to write the PTD entry when we add or initialize?
Correct. When you, for example, create this page
For this, you need a UVN.
well, in any code, like specifically the function which does it is this one, map pages. So map pages will take the page, the root of the page table, and take a physical address, which will be mapped at virtual address 0. So in this example, since we are not talking about, we can talk about this EUTVL, but essentially we also take virtual address 0, and we say, look, what's the machine address? Machine address is some address which, like, one of those pages which belong to us. And now we need to traverse the page table, and this code which is inside map pages. Let's go inside and quickly take a look at it. So implementation of map pages, essentially what it just does this walk page table directory. So essentially for every address, from every virtual address we want to map, it will walk the page table, potentially allocating those additional second level like pages for the page table, and then essentially returns the address of this entry. We cannot do it directly here because the page table is guarded by the host kernel, right? So we cannot allow the guest kernel to write the page table directly. Instead, we have to come up with a set of system calls which provide the same functionality for the guest kernel, but in a protected manner, meaning that every time the guest wants to update something, we will verify the security of this update. So the page has to belong to the guest. The guest can only map like the lower from 0 to 128, and it can map anything to that range, but then it's up to the guest to crush, right? And also we have to solve this problem that if the intermediate level doesn't exist, probably the guest should be responsible for allocating this page is allocated. And my suggestion here is that the guest who has to explicitly allocate the entries first by mapping the second level, but it can be done essentially.
Yeah, I remember the SV6 had a parameter, right? 0 is
correct, whether you want to allocate those levels or not.
Yeah.
And so it's essentially we're writing the code which is equivalent to this one plus this walk page table directory, which navigates it through a collection of system calls. Question.
So in this approach, yes. And
Correct. So this guest is paravirtualized. We're changing. It's fully aware that it's running on top of our virtual machine interface. And hold on, I thought that it was clear when we were talking about setting the address spaces, because the address space layout is different. So it's already knows. Okay, so this address space layout was done by this magical exact PVM, or whatever I call it, PVM system call, right? But this is more explicit. You say, look, I will have to rewrite this code. This function, by the way, it probably exposes the same interface. You can say, look, I have a pointer to the page directory. I have a virtual address, which I take. I have a unit size, physical address, size of the region I'm mapping, and permissions. And that's how per virtualization looks like. You say, you take this function to the rest of the kernel. This function looks the same. Don't really care. Nothing has changed. Ideally, you keep your changes minimal, right? And internally, you kind of implement this kind of, what is it called? Jigsaw interface, which instead of writing in a page table directly, because that's not allowed, we'll use those system calls like write PTD entry, write PT entry, and essentially like this function walk page table directory internally. Like I would assume that it's right here. Oh, again, man. This function. So, for example, it says, okay, I wanna do this tree. Okay, the page table is here. It's read only, so we can read it. So this line specifically may not have to change a lot, right? Because you have a pointer to the page table, right? However, writing, so like for example, this, you read it, you see, is there a next level? Okay, we have to allocate, but we cannot write directly in the PTD page table, page directory entry direct. This is not allowed because it's read only. So here you will stick a system call, which goes into the host kernel. Also takes like instead of it will take not a physical address, but from this table. Imagine you pick this table to this page to map. In this array which we introduced, it will contain a machine train number. So you can pass it to the host kernel to say, look, map this machine train number. But the host will verify that it's truly yours. And that the mapping which you're trying to install in the page table, meaning that those entries in this page table, I have to zoom in a little, but in this page table, you're not trying to overwrite memory of the host itself. You're writing below the 1 GB plus 128, right? All the entries above will be rejected, for example. And the host will say exception.
Okay, so this may be just a term. I always thought.
No,
But
man, that's because you missed half of the classes. Okay, can anyone answer the question? What is per virtualization and how it compares to trap and emulate? Thanks God, you know it. Otherwise, you know, I'm quitting. Okay, sorry. It does what? Say again. So yes, exactly. So Jerry, so trap and emulate is full virtualization. There was this group of people, like specifically, I think it's two, but maybe their work was based on some other work. Their names were like, I think Popak and Goldberg. Can mispronounce, apologize in advance. They wrote this paper that in order to virtualize something, you have to trap and emulate. Every time you write into the page table, it will catch a trap, go to the virtual machine monitor, and you will do whatever the writing emulation, right? Okay, that was kind of it wasn't that it was the stigma, but they were thinking that it's the best way to do something. But unfortunately, it's too expensive. And I mean, we were doing it in case of like, in fact, no one was doing it because VMware was not using trap and emulate. They were parsing the instruction stream, detecting those accesses early. Maybe they were doing a little bit of it, but majority of it was rewritten to do an explicit call into the hypervisor. If you're doing like a box style simulator, like you obviously don't trap and emulate, you just simply interpret each instruction. However, as we saw a couple of, like maybe last week, box is a little slower than QEMU with JIT compiler, but QEMU or VMware JIT compiler was fine for desktops. When I was your age, I was running Windows on top of FreeBSD because that was my setup, for example. But occasionally I had to run Word, right? And it was using JIT compilers. But for the data center, because when you're counting millions or billions, this overhead of 10 to 20% was high because it's a ton of money. And this group from Cambridge came up. I mean, there was first maybe a project from Utah I think it was called Denali, which was introduced this principle that you say, look, if you change the interface of your kernel, you're trading the development complexity, meaning that you have to change and think about how to do those changes. But then your stuff runs much faster than trap and emulate. And so the first practical system, which was deployed in data centers, was called Xen. And it's a project from Cambridge. And I think if I remember the history correctly, the relationship was that an intern from Cambridge went to Microsoft Research and built a power virtualized version of Windows. But maybe Cambridge already had a power virtualized version of Linux in-house first, most likely. Then they went to build the Windows, power virtualized Windows, and then Xen as a company started, and they the first Amazon cloud was essentially built around this solution. And now, this is how you convince the hardware manufacturers to do something. You show them the benefit. They said, okay, whoever can simplify the goal of power virtualization by providing set of hardware extension, but we're going to win the market because it's again, runs a little faster, less effort, runs Windows. And now majority of VMs actually combine elements of power virtualization, especially device driver interface. It's still trap and emulate is too expensive. So device drivers, when you install virtual machine monitor, you say something like install VMware tools. That essentially installs power virtualized device drivers, which you reuse those ring buffers for communication into the Windows system as device drivers. And then it runs. But essentially today we run elements of power virtualization plus VTX, which is Intel came up with this hardware supported virtualization. But proper term is hardware supported virtualization, or we call them HVM, hardware virtual machines. Our virtual machines we call PVM, and there is HPV, which Xen uses. It's a combination of hardware virtualization and power virtualization, because there is don't exactly remember at what specific moment, but there's this combination is faster than the other question. Or someone.
Yeah, just to finish the PTD entry, that's for the lock the page table. And is that just an allocate? You never use that.
Well, no, again, maybe my exposition was a little contrived, but at a high level, your goal as a system designer is to look at this code and think, okay, what needs to change? Sometimes you have to rewrite all of it, but sometimes not much. I'm kind of guessing that if you have read-only access to the page table directory, this line can stay. You don't have write access to the page table directory, so you have to replace it with a syscall. Here, you already and when you allocate, you write. So essentially, you kind of want to expose an equivalent interface to what this code is doing. So you have to walk the page table. You can walk it because you have a read-only access. But if you want to modify it, then you need a system call. And my story, which was again maybe a little bit contrived was for how to name the entries. And maybe you can you cannot use this actual address because the host has to verify your access. And if you just give the host a random address, the host is confused. The host is saying, okay, what's the relationship between these two? Because maybe it's a page of a different page table, which is probably okay, but I mean, you at least need to distinguish the root from the page table directory from the page table level. It looks like to me, but maybe some optimizations are possible. That's why I'm saying that when you want to write an entry, you have to explicitly provide the root. So the host immediately checks the association between the two and says, okay, in this page table, it leads here. So those two are connected. That's sound. And then you're writing this entry. That's okay, because those pages, we know. Why do you need to check this? Because you have to check that those are read-only to you. Otherwise, you will immediately change the page table, right? Read-only to the guest. And so this association is explicit in my system call. So it's kind of like it takes the root, it takes the page table level, and it takes the entry itself as the third argument, maybe the flags or something. So, but that's the high level story, which is conceptually, despite the fact that I'm kind of going in circles here, it's kind of not as hard, right? So it was a little hard, and it was a little hard for me to figure out the setup, like how do we want to have the virtual memory set up with respect to the rest of the system? How do we want to run processes? Like, what is the kernel process? What is the user process? How do we want to switch between them? But the moment you figure it out, it's kind of like building on top of that model, right? And I don't think it's super hard. So you say, look, the guest manages its own page tables. When it creates a new one, it registers with the host. Host marks the root as a read-only, sets everything to 0. When the guest switches from one to another, then explicitly like will be a context switch. And then we can, like in your homework, you have to come up with how to access, I mean, since I'm running out of memory, how to access devices, IO, not very hard, most likely just explicit system call to the host, like whatever, console write, keyboard read, how to inject the interrupts into the guest, and of course, how to do a syscall between the guest process and a host process. Not hard either. So you probably will go into the host kernel. Host kernel will switch a page table. It remembers the page table of the kernel and upcall, because you already know how to inject interrupts. So it shouldn't be that hard. But in a way, kind of interesting. And I mean, I cannot assign it as a coding assignment, but I will assign it as the write-up. And I think I told you enough in this lecture, so you can start, and it's not like out of the blue, so you have enough context to finish. That's my understanding, or that's my intent. Okay, you were sleeping for half a lecture, but now you woke up, which means you understood, which is great, I hope. Okay, any other questions?
Just on top of this. Let's say I have somebody who runs. So somebody have to say I want to run.
If you want to run Linux here.
Right. So
Yeah.
somebody has to there would be like a version of error.
Correct.
Go with that, and if you have different hyperware.
Yeah, correct. Yeah, correct. And the history, I will just take 2 more minutes of your time. The history was that Xen was the first power virtual hypervisor. They for many years, it was not in the main line of Linux. So they literally, they were supporting a version of Linux, which was capable of running from Xen. Linux moves forward. And periodically, they move from kernel 2.4 to 2.6, updating it. You cannot run anything else on Xen. And so it was kind of out of sync and a lot of effort. Then they said, okay, then the industry interest started building up, and the industry pushed on them and said, okay, I assume I don't know the details. Let's come up with a power virtualized standard. And then essentially each hypervisor, which the standard was obviously influenced by Xen, right? But each power virtual hypervisor can implement the standard, and the kernel can implement the standard. And at this point, this was merged into the Linux kernel. So right now, the Linux kernel out of the box comes to implement this standard, so you can run any version. But I mean, there are maintainers which maintain. But again, I think the only power virtual hypervisor is still Xen, but maybe there are some other minor layers in that. But that's the history. But yes, you really have to do it. And so the Cambridge team did it for Linux. Specifically, remember Keith Rather, Fraser, who never shows up. He's probably a genius in terms of cutting Linux apart. Imagine how much knowledge you need to we're doing it for x86. Okay, like for us, x86 is what is it, 10,000 lines of code. Linux, even back then, was at least a couple of millions. It's a little tricky. A question?
Yeah, so QU is. I can think of just one data.
Correct. Okay, so man,
That's probably
yeah.
too long.
I mean, I appreciate the interest. If you okay, 2 more minutes. QEMU, original QEMU was doing JIT compilation, meaning that it was parsing the instruction stream of the guest from block to block, then chaining, translating the instruction, putting them in a cache, and chaining the blocks together between like, so they were executing on top of this trace cache. And this compilation step was compilation, like just in time compilation. If you see something like move CR3 here, you immediately translate it in an explicit call to the hypervisor to say like, do something with my page tables. And do something will probably be kind of similar. Again, you will have to like either run it in the same memory or pick two processes and switch between them, something along those lines, right? That was original QEMU setup, right? And that was in the paper comparing hardware and software virtualization techniques. So maybe you go ahead and maybe read it again, not the whole paper, maybe just like a couple, first 3 pages, you understand. And then they moved to hardware supported virtualization, which the hardware just emulates a private copy of a CR3 for the guest inside. And this is the de facto standard now. But I wanted you to understand all of it essentially. That's why, okay, back to my ski tuning story. If you just say QEMU, my goal was for you to kind of dig into it to kind of get the feel of what's involved. That's kind of my hand tuning of my scheme, which is then hypervisor versus like let's say QEMU, because you can't even understand what QEMU is doing until you start doing something like that to make sure that you now I have to build it. Okay, sorry, yeah, you have to run. I apologize for running over. Just I could have answered next time, but then Jared would be sleeping. Hey, by the way, I'm traveling Monday, so the lecture will be on Zoom. I'll send an explicit reminder attending the SOSP. Okay, thank you so much, everyone. Sorry for being late.
So,